Have you ever wondered what it would be like to encounter a creature so bizarre that it would challenge everything you thought you knew about predators? Picture this. You're walking through an ancient forest, and suddenly you come face to face with a dinosaur that looks like it was designed by someone who had never seen a proper carnivore before. Its arms end in massive curved claws that seem completely impractical for hunting. Its body is bulky and pot-bellied like a walking refrigerator, and instead of razor-sharp teeth, it has a beak. You probably think you are hallucinating. Well, get ready to have your mind completely blown, because these creatures actually existed, and they represent one of the most fascinating evolutionary puzzles in paleontology. I'm talking about some of the weirdest, most wonderfully bizarre dinosaurs that ever walked the earth. Dinosaurs with claws so strange, so seemingly impractical, that scientists spent decades arguing about what they could possibly be used for. In this deep dive exploration, we're going to uncover the incredible stories behind these clawed mysteries. We'll journey through time to meet creatures that wielded talons longer than baseball bats, discover dinosaurs so small they could fit in your backpack, yet possessed proportionally enormous claws, and explore species that completely rewrote our understanding of what it means to be a predator. But here's the thing that will absolutely blow your mind. Most of these fearsome-looking creatures weren't hunters at all. I've spent months researching these incredible animals, diving deep into the latest scientific discoveries and controversial debates that have shaped our understanding of these enigmatic creatures. What I found will challenge everything you think you know about dinosaur evolution and reveal how nature can create solutions so bizarre they seem almost alien. But before we dive into these incredible stories, let me share something that perfectly captures just how strange these animals really were. When paleontologists first discovered some of these creatures, they were so baffled by what they found that they literally thought they had uncovered the remains of giant prehistoric turtles. The claws were so massive and so unlike anything they had seen before that it took decades of additional discoveries to piece together what these animals actually looked like and how they lived. Now, you might be thinking that weird claws are just weird claws, but trust me, the diversity of bizarre adaptations we're about to explore is absolutely staggering. We're talking about evolutionary experiments that pushed the boundaries of what's possible in the animal kingdom. Some of these creatures developed claws that were more like precision tools than weapons, while others grew appendages so large they could barely lift them. And perhaps most remarkably, some species took the concept of specialized claws so far that they essentially gave up having hands altogether, reducing their digits down to a single oversized talon. The story begins in the dusty badlands of Mongolia, where some of the most important paleontological discoveries of the 20th century were made. Picture vast desert landscapes punctuated by towering rock formations, where ancient secrets lie buried beneath layers of sandstone and time. It was here that scientists first encountered evidence of creatures so strange that they would spend the next several decades trying to figure out what they had found. These weren't your typical sharp-toothed, razor-clawed predators that most people imagine when they think of carnivorous dinosaurs. Instead, these were animals that seemed to defy every rule about how predators should look and behave. They had massive, powerful bodies built more like tanks than hunters, yet they possessed some of the most impressive claws ever discovered in the fossil record. What makes this story even more incredible is how our understanding of these creatures has completely transformed over the years. Early researchers, working with limited fossil evidence, came up with theories that now seem almost comically wrong. But as more discoveries were made and new technologies allowed scientists to peer deeper into the mysteries of these ancient bones, a picture emerged that was far stranger and more wonderful than anyone could have imagined. The first group of these bizarre creatures we need to talk about are the Alvarez-Rs. And let me tell you, these little guys were absolutely fascinating. Imagine a dinosaur about the size of a house cat, weighing roughly the same as a guinea pig, yet equipped with proportionally enormous claws that would make Wolverine jealous. These weren't massive beasts. We're talking about animals that you could easily pick up and carry, yet they possessed some of the most specialized and unusual arm adaptations in the entire dinosaur family tree. What made these creatures so remarkable wasn't just their size, but their incredible degree of specialization. While most dinosaurs retained the typical pattern of having multiple functional fingers on each hand, these little predators took a completely different evolutionary path. They essentially put all their eggs in one basket, so to speak, developing a single massive digit, while their other fingers either became tiny vestigial structures or disappeared entirely. But here's where things get really interesting. When scientists first started finding fossils of these creatures, they made a discovery that seemed to contradict everything they thought they knew about small predatory dinosaurs. These animals had inner ear structures that were remarkably similar to those found in modern barn owls. Think about that for a moment. We're talking about dinosaurs that lived over 60 million years ago, yet they had evolved sensory adaptations that mirror those of some of today's most efficient nocturnal hunters. This discovery led researchers to completely rethink how these animals lived and hunted. Instead of being simple daytime predators that relied on speed and agility, it appeared that these creatures were sophisticated nighttime hunters, equipped with extraordinary hearing abilities and possibly even specialized feather arrangements around their faces to help focus sound, just like modern owls. The evidence for feathers in these creatures opens up another incredible chapter in their story. We're not just talking about simple hair-like coverings either. Fossil evidence suggests that these dinosaurs possessed complex feather structures, including longer, more elaborate plumes that were likely used for display purposes. Imagine these tiny clawed hunters not only stalking through ancient forests in complete darkness, but also engaging in elaborate courtship displays with their colorful plumage. Now you might be wondering exactly what these creatures were using their oversized claws for. This question has led to some of the most heated debates in paleontology, with scientists proposing theories ranging from the practical to the seemingly absurd. Some researchers suggested that these claws were perfect tools for breaking into insect nests, particularly termite mounds, allowing these small predators to access protein-rich food sources that other animals couldn't reach. But other scientists weren't convinced. They pointed out that the claws, while impressive, might not have been sturdy enough for the kind of heavy-duty digging that would be required to break open well-constructed termite colonies. Instead, they proposed that these appendages were used more like precision instruments, allowing the dinosaurs to probe into crevices and extract small prey items like insects and possibly even small mammals. The plot thickens when we consider the incredible diversity within this group of clawed dinosaurs. While some species retained small vestigial second and third digits alongside their massive primary claw, others took specialization to an even more extreme level. There were species that completely eliminated all but one functional digit on each hand, creating what was essentially a living ice pick attached to a small feathered body. One of the most remarkable things about these creatures is how they managed to thrive in some of the harshest environments on Earth. The fossil record shows us that many of these species lived in what are now desert regions, areas that during their time period would have been characterized by extreme temperature variations, limited water sources, and sparse vegetation. Yet these small, specialized hunters not only survived in these challenging conditions, but apparently flourished. The success of these creatures in such demanding environments tells us something profound about the power of evolutionary specialization. Rather than trying to be generalists that could handle a wide variety of challenges, these dinosaurs became incredibly good at doing one specific thing. Their entire body plan, from their enhanced sensory systems to their specialized claws, was focused on a particular lifestyle that allowed them to exploit ecological niches that other predators couldn't access. As we delve deeper into the fossil record, we discover that these clawed hunters weren't just successful in one particular region or time period. Evidence of their presence has been found across multiple continents, suggesting that their unique adaptations were successful enough to allow them to spread across vast geographic ranges. This global distribution also provides us with fascinating insights into how continents and ecosystems were connected during the Age of Dinosaurs. But perhaps the most mind-blowing aspect of these creatures is what they tell us about the relationship between dinosaurs and modern birds. The more we learn about these ancient clawed hunters, the more we realize that they represent crucial links in understanding how dinosaurs evolved into the birds we see today. Their feather structures, their sensory adaptations, even their bone density and respiratory systems all provide clues about the incredible transformation that led from massive prehistoric reptiles to the diverse array of flying creatures that fill our skies today. The story of these bizarre clawed dinosaurs is far from over. New discoveries are being made regularly, each one adding another piece to the puzzle of how these remarkable creatures lived, hunted, and evolved. Some of the most recent findings have revealed species with even more extreme adaptations, pushing the boundaries of what we thought was possible in terms of claw specialization and body plan modification. What's even more incredible is that as we move beyond these tiny owl-like hunters, we encounter an entirely different branch of clawed dinosaurs that took the concept of bizarre appendages to absolutely mind-boggling extremes. We're talking about creatures that would make the small alvarezars look like delicate precision instruments in comparison. Enter the world of the Therizinosaurids and prepare to have your understanding of what constitutes a fearsome predator completely shattered. These weren't small cat-sized creatures skulking through the night. No, these were absolute giants, some reaching lengths that would dwarf modern elephants. Yet they possessed claws that were so massive, so seemingly impractical, that when scientists first discovered them, they literally had no idea what kind of creature could have produced such enormous talons. Picture this. You're a paleontologist working in the harsh, windswept Badlands, carefully excavating what you believe might be the remains of an ancient turtle. You brush away layer after layer of sediment, and suddenly you uncover what appears to be a claw that's longer than your entire arm. Not just slightly longer. We're talking about appendages that could reach over 50 centimeters in length, curved like massive scythes, and built with a robustness that suggests they could have been used to tear through just about anything. The initial reaction of the scientific community to these discoveries was nothing short of bewildered. Here were claws that seemed designed for the ultimate predator. Yet, as more fossil evidence emerged, a picture began to form that challenged every assumption about what these weapons were actually used for. The bodies attached to these fearsome talons weren't built like killing machines at all. Instead, they had the proportions of something that looked more like a walking barn than a sleek hunter. These creatures had massive pot-bellied torsos that could house enormous digestive systems, long necks that seemed better suited for reaching high vegetation than lunging at prey, and relatively small heads equipped not with rows of razor-sharp teeth, but with big mouths that looked suspiciously similar to those of modern herbivorous birds. It was as if someone had taken the most intimidating claws in the fossil record and attached them to the body of a creature that seemed designed for peaceful browsing rather than violent predation. The mystery deepened when researchers began to analyze the bone structure and joint mechanics of these enormous appendages. Biomechanical studies revealed that while these claws looked like they could slice through just about anything, they were actually quite fragile when subjected to the kinds of stresses that would be involved in attacking prey or defending against predators. The bones showed stress patterns that suggested these appendages were simply not built for combat. So what on earth were these massive talons actually used for? This question sparked debates that raged through the paleontological community for decades, with scientists proposing increasingly creative theories about the function of these bizarre structures. Some suggested that they were used like massive grappling hooks, allowing these creatures to pull down high branches loaded with nutritious leaves and fruits. Others proposed that they served as intimidation displays, visual signals that could ward off potential threats without the need for actual physical confrontation. But perhaps the most fascinating theory emerged when researchers began to study the feeding habits and digestive systems of these creatures more closely. Evidence began to mount that these fearsome-looking giants were actually among the most peaceful dinosaurs that ever lived. Their teeth, when present at all, were adapted for cutting and grinding plant material rather than tearing flesh. Their digestive systems were enormous, suggesting the need to process large quantities of relatively low nutrition plant matter. The realization that these massive claw-bearing dinosaurs were actually herbivores represents one of the most dramatic paradigm shifts in our understanding of prehistoric life. Here were creatures that looked like they should have been apex predators, yet they had evolved to fill the ecological niche of gentle giants, using their impressive size and intimidating appearance as a form of passive defense while they peacefully browsed on ancient vegetation. This discovery opened up entirely new questions about the evolution of defensive strategies in dinosaurs. If these creatures weren't using their claws for hunting, and biomechanical analysis suggested they weren't particularly effective as weapons, then what advantage did possessing such massive appendages provide? The answer seems to lie in the complex social and ecological dynamics of prehistoric ecosystems. Living alongside these gentle giants were some of the most formidable predators that ever walked the earth. We're talking about massive carnivorous dinosaurs with bone-crushing jaws and lightning-fast reflexes, creatures that could easily overpower most herbivores through sheer predatory skill. In this environment, the development of impressive defensive displays could mean the difference between life and death. Imagine being a hungry predator and encountering one of these massive clawed herbivores for the first time. Even if you somehow knew that those enormous talons weren't particularly effective as weapons, the sheer visual impact of seeing a creature the size of a bus wielding claws longer than baseball bats would probably give you serious second thoughts about whether this particular meal was worth the risk. But the story of these bizarre clawed herbivores becomes even more remarkable when we consider the incredible diversity of forms they evolved. Some species developed relatively modest claws alongside more traditional herbivorous adaptations, creating creatures that represented transitional forms between typical predatory dinosaurs and the extreme specialists we've been discussing. These intermediate species provide us with incredible insights into how such dramatic evolutionary changes can occur over time. Other species took the concept of claw specialization in completely different directions. Instead of developing massive, intimidating talons, some lineages evolved claws that were clearly adapted for precision work. These creatures had appendages that looked more like sophisticated tools than weapons, with shapes and proportions that suggested they were used for delicate manipulation of their environment, rather than dramatic displays or defensive purposes. The fossil record reveals species with claws that were perfectly curved for stripping leaves from branches, others with straight, pointed talons that seemed designed for probing into crevices or breaking open tough plant materials, and still others with broad, flattened claws that might have been used for digging or processing food in ways we're only beginning to understand. What makes this diversity even more remarkable is that it all evolved within a relatively short geological time frame. We're talking about an evolutionary explosion of claw specialization that produced dozens of different solutions to the challenges of surviving as a large herbivore in a world dominated by massive predators. Each species found its own unique way to use these appendages, creating an incredible array of forms that showcases the creative power of natural selection. The feather evidence for these creatures adds yet another layer of fascination to their story. Fossil impressions show that many of these species were covered in complex plumage that included both simple, hair-like structures for insulation and elaborate, colorful feathers that were almost certainly used for display purposes. Imagine these massive clawed herbivores, not only using their impressive size and intimidating appendages for defense, but also engaging in elaborate courtship rituals involving spectacular feather displays. The color analysis of preserved feather structures has revealed that some of these creatures sported dark, earth-tone plumage that would have provided excellent camouflage in their forest environments, while others had more vibrant coloration that suggests they lived in more open habitats where visual communication over long distances would have been important. These discoveries completely revolutionize our understanding of what life was like in prehistoric ecosystems. Instead of the simple predator-prey relationships that we often imagine, we're seeing evidence of complex social behaviors, elaborate communication systems, and sophisticated survival strategies that rival anything we see in modern animal communities. The more we learn about these clawed herbivores, the more we realize that they represent one of the most successful evolutionary experiments in the history of life on Earth. Despite their seemingly impractical appendages and bizarre body proportions, these creatures thrived for millions of years across multiple continents, adapting to a wide variety of environmental conditions and ecological niches. Their success challenges our assumptions about what makes an effective survival strategy. Instead of developing speed, agility, or traditional defensive weapons, these creatures invested in size, intimidation, and specialized feeding adaptations that allowed them to exploit resources that other herbivores couldn't access. It's a testament to the incredible creativity of evolutionary processes and a reminder that nature often finds solutions that seem completely counterintuitive to our human perspective. As we continue to uncover new fossils and develop better analytical techniques, our understanding of these remarkable creatures continues to evolve. Recent discoveries have revealed species with even more extreme claw adaptations, pushing the boundaries of what we thought was possible in terms of appendage specialization and creating new puzzles for paleontologists to solve. The story of these clawed dinosaurs is far from complete, and each new discovery adds another piece to the incredible puzzle of how life on Earth has adapted and evolved over hundreds of millions of years. What's clear is that these creatures represent some of the most remarkable examples of evolutionary innovation in the fossil record, and their legacy continues to influence our understanding of how complex ecosystems function and evolve over time. But what happens when we push the boundaries of claw specialization even further? What if I told you that some dinosaurs took this concept so far that they essentially redesigned the entire structure of their hands, creating appendages so bizarre that they seem like something out of science fiction? Meet the most extreme members of this clawed dynasty, creatures that represent the absolute pinnacle of appendage specialization in the dinosaur world. We're talking about animals that didn't just develop impressive claws, they completely revolutionized what it means to have hands in the first place. Picture a dinosaur that looks relatively normal from behind. You've got the typical bipedal stance, the long tail for balance, the powerful leg muscles that suggest this creature was built for speed. But then it turns around, and you're confronted with something that defies all logic. Instead of the five-fingered hands that most early dinosaurs possessed, or even the three-fingered arrangement that became standard among theropods, this creature has reduced its entire hand down to essentially a single massive digit. This isn't just a case of some fingers being smaller than others. We're talking about complete elimination of functional digits, leaving behind what amounts to a living spear attached to muscular arms. The evolutionary pressure required to drive such extreme specialization must have been absolutely incredible, representing millions of years of refinement toward a single specific function. When paleontologists first encountered evidence of these ultra-specialized creatures, they faced a puzzle that seemed almost impossible to solve. Here were dinosaurs that had essentially given up one of the most versatile and useful anatomical features in the animal kingdom, the multi-fingered hand, in favor of what appeared to be a highly specialized tool whose purpose was completely mysterious. The fossil evidence revealed creatures that were surprisingly small, some no bigger than modern chickens. Yet they possessed proportionally enormous claws that dominated their entire body plan. These weren't massive, intimidating herbivores using their appendages for display purposes. These were compact, agile creatures whose entire evolutionary strategy seemed focused around the perfect execution of some highly specific task. But here's where the story takes an absolutely fascinating turn. As researchers began to study the bone structure and joint mechanics of these extreme specialists, they discovered something remarkable. The arms and shoulders of these creatures were incredibly robust, far more muscular and powerful than what you'd expect for animals of their size. This suggested that whatever they were using their single-clawed hands for, it required tremendous strength and precision. The mystery deepened when scientists began analyzing the wear patterns on fossilized claws from these creatures. The evidence suggested that these appendages were being used for repetitive, forceful actions that created distinctive scratches and stress marks on the bone. This was clearly not random damage from everyday activities. These claws were being used as sophisticated tools for some very specific purpose. One of the most compelling theories that emerged from this research was that these ultra-specialized dinosaurs had evolved to become the ultimate insect hunters. Their single powerful claws weren't weapons or display structures. They were precision excavation tools perfectly designed for breaking into the hardened nests of social insects like termites and ants. Think about the engineering challenges involved in such a lifestyle. Social insects build some of the most sophisticated defensive structures in the natural world, creating colonies that can withstand attacks from much larger predators. To successfully exploit this food source, a predator would need incredible precision, tremendous strength, and the ability to work quickly before the insects could mount an effective defense. The fossil evidence suggests that these specialized dinosaurs had solved all of these challenges through their extreme anatomical adaptations. Their single claws provided the precision needed to target specific weak points in insect colonies, while their powerful arm muscles delivered the force required to break through even the most well-constructed defenses. But perhaps most remarkably, these creatures had evolved sensory systems that were perfectly matched to their hunting strategy. Fossil skulls reveal inner ear structures that were incredibly sophisticated, suggesting these animals possessed hearing abilities that rivaled those of modern nocturnal hunters. They could probably locate insect colonies by sound alone, detecting the subtle vibrations and acoustic signatures that would reveal the location of hidden nests. The night vision capabilities of these creatures were equally impressive. Analysis of their eye socket structures suggests they possessed enlarged pupils and specialized retinal arrangements that would have allowed them to hunt effectively in complete darkness. Combined with their extraordinary hearing, these adaptations would have made them absolutely devastating predators in their specialized niche. What makes this story even more incredible is that these extreme specialists weren't just successful in one particular environment or time period. Fossil evidence shows that similar creatures evolved independently in multiple locations around the world, suggesting that the ecological pressures that drove such extreme specialization were widespread and persistent throughout dinosaur history. The global success of these ultra-specialized hunters tells us something profound about the nature of evolutionary innovation. Sometimes the most effective strategy isn't to be a generalist that can handle a wide variety of challenges, but to become so incredibly good at one specific thing that you can exploit resources that no other creature can access. This principle becomes even more apparent when we examine the incredible diversity of specialized forms that evolved within this group. While some species developed the single-clawed arrangement we've been discussing, others took different approaches to the same basic challenge. Some retained vestigial second and third digits alongside their primary claw, creating multi-tool arrangements that combined the precision of specialized equipment with the versatility of more traditional hand structures. Other species evolved claws with completely different shapes and proportions, suggesting they were targeting different types of prey or using different hunting techniques. Some developed straight pointed claws that were perfect for probing into narrow crevices, while others had curved talons that seemed designed for hooking and tearing actions. The fossil record even reveals species that appeared to use their specialized claws in coordinated attacks, working together to overcome prey that would have been too challenging for a single individual to handle. This suggests that some of these creatures had evolved complex social behaviors and hunting strategies that allowed them to tackle much larger and more difficult targets than their size would normally permit. But as we move beyond these small, specialized insect hunters, we encounter yet another chapter in the story of bizarre clawed dinosaurs, creatures that took the concept of appendage modification in completely different directions. These weren't tiny precision hunters or massive, intimidating herbivores. Instead, they represented something entirely new, medium-sized omnivores that had developed claws for purposes that scientists are still trying to fully understand. These intermediate forms provide us with crucial insights into how such extreme specializations can evolve over time. Rather than jumping directly from typical theropod hands to the ultra-specialized single-claw arrangement, evolution appears to have proceeded through a series of gradual modifications, each one representing a step toward greater specialization. The transitional fossils show us dinosaurs with 3 functional fingers, but with 1 digit that was beginning to dominate the others in size and robustness. Other specimens reveal creatures where the 2nd and 3rd fingers were becoming progressively smaller and less functional, while the primary digit continued to grow larger and more specialized. This evolutionary sequence provides us with a rare glimpse into how major anatomical changes can occur through gradual modification rather than sudden, dramatic shifts. Each intermediate form would have been perfectly adapted to its own particular ecological niche, while also representing a step along the path toward even greater specialization. The dietary evidence from these transitional forms is particularly fascinating. Stomach contents and coprolite analysis suggests that these creatures were opportunistic feeders, taking advantage of whatever food sources were available in their environments. Some specimens contain evidence of plant material, suggesting they supplemented their diet with fruits, seeds, and other vegetation. Others show clear signs of insect consumption, with fragments of chitinous exoskeletons preserved in their digestive systems. This dietary flexibility appears to have been a key factor in the evolutionary success of these creatures. By maintaining the ability to exploit multiple food sources, they could survive in environments where more specialized species might struggle. This adaptability may have provided the evolutionary foundation that allowed their descendants to develop even more extreme specializations. The feather evidence from these transitional forms adds another layer of complexity to their story. Fossil impressions reveal that many of these species possessed elaborate plumage that included both functional feathers for temperature regulation and ornamental structures that were clearly used for display purposes. The display feathers are particularly interesting because they suggest that these creatures engaged in complex social behaviors despite their relatively small size. Color analysis of preserved melanosomes indicates that some species had incredibly vibrant plumage, with patterns and hues that would have been visible from considerable distances. This evidence for Sophisticated social communication challenges our assumptions about how these specialized hunters lived and interacted with each other. Instead of solitary creatures focused entirely on their narrow feeding niche, we're seeing evidence of animals that maintained complex social structures and engaged in elaborate courtship and territorial displays. The implications of this discovery extend far beyond our understanding of these particular creatures. It suggests that even highly specialized predators can maintain the cognitive and social complexity necessary for sophisticated behavioral patterns. This challenges the old stereotype of specialized animals as simple, instinct-driven creatures, and reveals them to be far more behaviorally complex than we previously imagined. As we continue to uncover new fossil evidence and develop better analytical techniques, our picture of these remarkable creatures continues to evolve and expand. Recent discoveries have revealed species with even more unusual claw adaptations, including some that appear to have used their specialized appendages for purposes we're still trying to understand. One particularly intriguing recent find shows evidence of a species that had developed claws with internal hollow chambers, similar to the quills of modern porcupines. The function of these hollow structures is still being debated, but some researchers suggest they might have been used for sound production, allowing these creatures to communicate through acoustic signals that other animals couldn't detect or interpret. Another recent discovery revealed a species with claws that showed evidence of rapid seasonal regrowth similar to the antlers of modern deer. This suggests that at least some of these creatures were shedding and regrowing their primary appendages on a regular basis, possibly in response to breeding cycles or seasonal changes in their environment. These discoveries continue to expand our understanding of just how creative and diverse the evolutionary solutions to survival challenges can be. Each new fossil adds another piece to the puzzle of how these remarkable creatures lived, hunted, and evolved over millions of years of Earth's history. The story of these clawed dinosaurs represents far more than just an interesting footnote in paleontological research. These creatures demonstrate the incredible power of evolutionary specialization and show us how life can find success through strategies that seem completely counterintuitive from our human perspective. Their legacy extends into our modern world through their descendants, the birds that fill our skies today. Many of the anatomical innovations we see in these ancient clawed hunters, from their feather structures to their respiratory systems, provided the evolutionary foundation for the incredible diversity of avian life that surrounds us. Every time you see a woodpecker using its specialized beak to excavate insects from tree bark, or watch an owl hunting silently through the night, you're witnessing the continuation of evolutionary strategies that were first perfected by these bizarre clawed dinosaurs millions of years ago. The research continues, and each new discovery brings us closer to understanding the full scope of their remarkable evolutionary achievements. What's clear is that these creatures represent some of the most innovative and successful solutions to survival challenges in the history of life on Earth, and their story continues to inspire and inform our understanding of how evolution shapes the incredible diversity of life around us. The incredible journey through these clawed mysteries takes yet another unexpected turn when we encounter creatures that pushed specialization beyond anything we've discussed so far. We're about to meet dinosaurs that didn't just modify their claws. They completely reimagined what it means to be a predator in the first place. Imagine stumbling across fossil evidence of a creature that weighed no more than a modern house cat, yet possessed claws that were proportionally larger than those of a grizzly bear. This isn't science fiction. This is exactly what paleontologists discovered when they first encountered the remains of some truly extraordinary small theropods. These weren't just unusual. They were so bizarre that they forced scientists to completely rethink their understanding of predator-prey relationships in prehistoric ecosystems. What makes these discoveries so mind-blowing is the sheer audacity of their evolutionary strategy. While most small predators relied on speed, agility, and pack hunting to survive in a world filled with giants, these creatures took a completely different approach. They became living precision instruments, so perfectly adapted to their specific ecological niche that they could exploit food sources that remained completely inaccessible to other predators. The fossil evidence reveals creatures whose entire body plan was subordinated to the function of their remarkable claws. Their shoulder girdles were massively overdeveloped relative to their body size, creating anchor points for muscles that could deliver tremendous force through their specialized appendages. Their arm bones showed stress patterns that indicated regular intensive use. These weren't display structures or occasional use tools, but rather appendages that were being employed constantly throughout these creatures' daily lives. But here's where the story becomes absolutely fascinating from a biomechanical perspective. When researchers began analyzing the joint mechanics and range of motion in these specialized arms, they discovered something remarkable. These creatures hadn't just developed powerful claws. They had evolved completely unique movement patterns that allowed them to use their appendages in ways that would have been impossible for more conventionally built predators. The shoulder joints showed adaptations that permitted an extraordinary range of forward motion, allowing these creatures to extend their claws far beyond what typical theropod anatomy would allow. This enhanced reach would have been crucial for accessing prey items hidden deep within crevices, burrows, or other protected locations that conventional predators simply couldn't reach. Even more remarkably, the wrist and finger joints displayed modifications that enabled incredibly precise control over claw positioning and movement. We're talking about adaptations that would have allowed these creatures to manipulate their environment with almost surgical precision, targeting specific weak points in prey defenses or navigating complex three-dimensional spaces with remarkable accuracy. The sensory adaptations that accompanied these mechanical modifications were equally impressive. Fossil skull analysis reveals that these creatures possessed extraordinarily well-developed inner ear structures, suggesting balance and spatial awareness capabilities that far exceeded what we see in most modern predators. This enhanced proprioception would have been essential for creatures that needed to use their specialized appendages Effectively, in challenging environments where a single miscalculation could mean the difference between a successful hunt and serious injury. Their olfactory capabilities were similarly enhanced, with enlarged nasal cavities and complex turbinate structures that would have allowed them to detect incredibly subtle chemical signatures in their environment. This heightened sense of smell would have been crucial for locating hidden prey, identifying the freshest and most vulnerable targets, and avoiding areas where larger predators might pose a threat. But perhaps most remarkably, these creatures appear to have evolved sophisticated echolocation abilities that rivaled those of modern bats and dolphins. The bone structure around their inner ears shows adaptations consistent with the production and reception of high-frequency sound waves, suggesting they could navigate and hunt effectively even in complete darkness, or in environments where visual hunting would have been impossible. This combination of mechanical precision, enhanced sensory capabilities, and sophisticated behavioral adaptations created predators that were incredibly effective within their specialized niche. The fossil record shows that these creatures were remarkably successful, with evidence of their presence found across multiple continents and spanning millions of years of evolutionary time. What's even more incredible is that this success came despite their apparent vulnerability to larger predators. These were small, relatively fragile creatures living in ecosystems dominated by massive carnivorous dinosaurs that could have easily overpowered them. Yet they not only survived, but thrived, suggesting that their specialized hunting strategies provided them with significant advantages that more than compensated for their physical limitations. The key to their success appears to have been their ability to exploit food sources that were completely inaccessible to larger predators. While massive carnivores were competing for large prey animals, these specialized hunters were tapping into entirely different energy sources: protein-rich insect colonies, small vertebrates hidden in complex burrow systems, and other resources that required precision and finesse rather than brute force to access. This ecological strategy had profound implications for prehistoric food webs. By exploiting these previously untapped resources, these specialized predators were able to support population levels that would have been impossible if they had been competing directly with larger carnivores. Their presence also likely had cascading effects throughout their ecosystems, controlling populations of social insects and small vertebrates in ways that influenced the entire ecological balance. The evolutionary pressures that drove such extreme specialization must have been absolutely incredible. We're talking about selection forces so intense and persistent that they completely reshape not just the anatomy, but the entire life history strategy of these creatures. Every aspect of their biology, from their sensory systems to their reproductive behaviors, became subordinated to the demands of their highly specialized hunting lifestyle. Evidence suggests that these creatures had evolved remarkably sophisticated behavioral repertoires to match their anatomical adaptations. Trackway fossils reveal complex movement patterns that indicate these predators were capable of incredibly precise maneuvering, including the ability to approach prey from multiple angles and coordinate their attacks with remarkable timing and accuracy. Some trackways even show evidence of cooperative hunting behaviors, with multiple individuals apparently working together to overcome particularly challenging prey. This suggests that despite their small size and specialized anatomy, these creatures had maintained the cognitive complexity necessary for sophisticated social coordination and strategic planning. The implications of this discovery extend far beyond our understanding of these particular species. It demonstrates that evolutionary specialization doesn't necessarily lead to behavioral simplification or reduced cognitive capacity. Instead, these creatures appear to have developed even more sophisticated behavioral capabilities as their anatomy became increasingly specialized. This challenges many of our assumptions about the relationship between physical specialization and behavioral complexity. Rather than being simple, instinct-driven creatures, these specialized predators appear to have been remarkably intelligent and adaptable, capable of adjusting their hunting strategies in response to changing environmental conditions and prey availability. The feather evidence from these creatures adds yet another layer of complexity to their already remarkable story. Fossil impressions reveal that many species possessed elaborate plumage arrangements that went far beyond simple temperature regulation or camouflage. Some had developed feather structures that were clearly adapted for acoustic purposes, possibly enhancing their echolocation abilities or providing new channels for intraspecific communication. Other species showed evidence of remarkably sophisticated display plumage, with complex patterns and structures that would have required significant metabolic investment to maintain. This suggests that even these highly specialized predators maintained active social lives that included elaborate courtship rituals and territorial displays. The color analysis of preserved melanosomes reveals that some of these creatures sported incredibly vibrant plumage with hues and patterns that would have been visible from considerable distances. This is particularly remarkable when we consider that many of these species appear to have been primarily nocturnal hunters. The investment in bright, conspicuous coloration suggests that visual communication remained important despite their specialized lifestyle. Recent discoveries have revealed even more extreme examples of claw specialization within this group. Some newly discovered species appear to have developed claws with internal structures that were even more complex than anything we've discussed so far. We're talking about appendages that contained multiple chambers, specialized ridges, and other modifications that suggest functions we're still trying to understand. One particularly intriguing recent find shows evidence of claws that contained what appear to be venom delivery systems, similar to those found in modern venomous snakes. If this interpretation is correct, it would represent the first evidence of venomous dinosaurs and would completely revolutionize our understanding of predator-prey interactions in prehistoric ecosystems. Another remarkable discovery revealed a species with claws that showed evidence of electrical sensitivity, similar to the electroreception capabilities found in modern sharks and rays. The functional implications of this adaptation in a terrestrial predator are still being explored, but it suggests that these creatures may have been able to detect the bioelectrical signatures of hidden prey, providing them with yet another sensory advantage in their specialized hunting niche. These ongoing discoveries continue to expand our appreciation for just how innovative and diverse the evolutionary solutions to survival challenges can be. Each new fossil reveals adaptations that push the boundaries of what we thought was possible in terms of anatomical specialization and behavioral complexity. The research techniques being applied to these fossils are becoming increasingly sophisticated as well. Advanced imaging technologies are allowing scientists to peer inside fossilized bones and reveal details about internal structures that were previously impossible to study. Chemical analysis of preserved organic compounds is providing new insights into the physiology and metabolism of these ancient creatures. Computer modeling and biomechanical analysis are helping researchers understand exactly how these specialized appendages would have functioned in life, revealing the incredible precision and efficiency of their evolutionary engineering. These studies are showing that the claws weren't just impressive-looking structures, they were sophisticated tools that represented millions of years of evolutionary refinement. The story becomes even more remarkable when we consider the environmental challenges these creatures would have faced. Many lived in harsh, semi-arid environments where food resources would have been scarce and competition intense. Their ability to exploit specialized food sources that other predators couldn't access would have provided them with crucial advantages during difficult periods. Climate analysis of their fossil-bearing formations reveals that these creatures survived through multiple episodes of environmental change, including periods of dramatic temperature fluctuation and ecosystem restructuring. Their specialized adaptations appear to have provided them with remarkable resilience in the face of these challenges, allowing them to maintain stable populations even when more generalized species were struggling. This environmental resilience has important implications for our understanding of how specialized species respond to ecological change. Rather than being evolutionary dead ends that are vulnerable to extinction when conditions change, these creatures demonstrate that extreme specialization can sometimes provide greater long-term survival advantages than more generalized strategies. The global distribution of these specialized predators also tells us important things about prehistoric biogeography and ecosystem connectivity. Evidence of similar creatures has been found on multiple continents, suggesting that the ecological pressures driving such extreme specialization were widespread and persistent throughout much of the Mesozoic era. This global pattern of convergent evolution demonstrates that the basic ecological niche exploited by these creatures was a fundamental component of prehistoric terrestrial ecosystems. The consistency of their adaptations across different geographic regions and time periods suggests that this specialized hunting strategy was not just successful, but virtually inevitable given the right environmental conditions. The evolutionary relationships between different lineages of these specialized predators are still being worked out, but current evidence suggests that extreme claw specialization evolved independently multiple times throughout dinosaur history. This repeated evolution of similar solutions to the same ecological challenges provides powerful evidence for the predictability of evolutionary processes under similar selective pressures. Some lineages appear to have achieved their specializations through gradual modification of existing structures, while others show evidence of more rapid evolutionary changes that produce dramatic anatomical innovations in relatively short geological time periods. This variation in evolutionary tempo and mode provides valuable insights into the factors that control the rate and direction of morphological change. The developmental biology of claw formation in these creatures is also yielding fascinating insights. Studies of growth patterns in juvenile specimens reveal that the extreme specializations we see in adults develop through complex interactions between genetic programming and environmental influences during development. Some species show evidence of dramatic shifts in growth patterns as individuals matured, suggesting that the transition to specialized hunting behaviors required significant physiological reorganization. These developmental studies are also revealing that the extreme claw specializations were accompanied by coordinated changes throughout the entire musculoskeletal system. The modifications weren't limited to the appendages themselves, but extended to the shoulder girdle, vertebral column, and even the pelvic region, creating integrated anatomical systems that were perfectly tuned for specialized predatory behaviors. The metabolic implications of maintaining such specialized anatomy would have been significant. The enlarged muscle masses and enhanced sensory systems would have required substantial energy investments, suggesting that these creatures needed access to high-quality food sources to sustain their specialized lifestyle. This metabolic constraint may have been one of the factors that limited their body size and influenced their ecological distribution patterns. Energy budget calculations based on their anatomy suggest that these creatures would have needed to be remarkably efficient hunters to maintain positive energy balances. This efficiency requirement may have driven the evolution of their sophisticated behavioral repertoires and enhanced sensory capabilities, creating positive feedback loops that pushed specialization to ever greater extremes. The social implications of their hunting strategies are also becoming clearer as more fossil evidence accumulates. Trackway sites showing evidence of group activities suggest that these creatures maintained complex social structures despite their specialized lifestyles. Some sites show evidence of coordinated hunting behaviors, while others indicate communal nesting or roosting activities. The maintenance of social cohesion in highly specialized predators presents interesting evolutionary challenges. These creatures needed to balance the advantages of cooperation with the constraints imposed by their narrow ecological niche. The solutions they evolved appear to have been remarkably sophisticated, involving complex communication systems and flexible behavioral strategies that allowed them to exploit their specialized niche while maintaining the benefits of group living. Evidence for parental care in these creatures is particularly intriguing. Some fossil sites preserve adult and juvenile specimens in close association, suggesting that parents may have actively taught their offspring the complex skills necessary for successful specialized hunting. This behavioral transmission of hunting techniques would have been crucial for maintaining the precision and efficiency required for their extreme lifestyle. The learning curve for mastering such specialized hunting techniques would have been steep, requiring extended periods of juvenile dependence and intensive parental investment. This life history strategy would have had profound implications for population dynamics and reproductive success, potentially limiting population growth rates, but enhancing individual survival and reproductive success. As we continue to uncover new evidence about these remarkable creatures, their story becomes increasingly complex and fascinating. What started as a simple tale of unusual claws has evolved into a comprehensive picture of some of the most sophisticated and successful evolutionary experiments in the history of life on Earth. These creatures demonstrate that evolution can produce solutions that seem almost impossibly specialized, yet prove to be remarkably successful when viewed from the proper ecological perspective. Their legacy continues to influence our understanding of predator-prey relationships, evolutionary specialization, and the incredible creativity of natural selection in solving survival challenges. The techniques and technologies we're using to study these fossils continue to advance, promising even more remarkable discoveries in the years to come. Each new analytical method reveals previously hidden details about their anatomy, behavior, and ecology, gradually building a more complete picture of how these extraordinary creatures lived and thrived in their ancient world. The story of these clawed dinosaurs is far from complete, and the next chapter promises to be even more remarkable as we uncover new species, develop better analytical techniques, and gain deeper insights into the evolutionary processes that created some of the most specialized and successful predators in the history of life on Earth. But as incredible as these small specialized hunters were, they represent just one branch of the great evolutionary tree of clawed dinosaurs. This story takes yet another dramatic turn when we encounter creatures that approach the challenge of survival with completely different strategies, developing claws that serve purposes so unusual and unexpected that they continue to puzzle paleontologists today. These weren't the precision instruments we've been exploring, nor were they the massive intimidation displays of the giant herbivores. Instead, we're about to encounter dinosaurs that developed claws for purposes so fundamentally different that they challenge our entire understanding of what these appendages can be used for. Meet the transitional giants, creatures that occupied a fascinating middle ground between the small specialists and the enormous browsers we've discussed. These were dinosaurs that stood roughly the height of a modern giraffe, yet possessed proportions that seemed almost comically mismatched. Picture a creature with the bulk of a rhinoceros, the neck of an ostrich, and arms that terminated in claws that looked like they belonged on a creature 3 times their size. What makes these intermediate forms so crucial to our understanding is that they represent evolutionary experiments in progress. These weren't the end products of millions of years of specialization, but rather creatures caught in the act of becoming something entirely new. Their anatomy tells the story of evolution in real time, showing us how radical changes in body plan and lifestyle can emerge through gradual modification of existing structures. The first thing that strikes you about these creatures is their sheer awkwardness. Everything about their proportions seems slightly wrong, as if they were assembled from parts belonging to completely different animals. Their heads were relatively small and delicate, equipped with beaks that suggested herbivorous feeding habits, yet they were supported by necks so long and flexible that they could reach vegetation that would have been impossible for other ground-dwelling herbivores to access. But it's when you examine their arms and claws that the true strangeness of these creatures becomes apparent. The appendages were massive relative to their body size, yet they lacked the obvious specializations we see in their more extreme relatives. The claws were impressive in their dimensions, certainly large enough to serve as formidable weapons, yet their shape and structure suggested they were being used for something entirely different. Biomechanical analysis of these intermediate forms reveals appendages that were optimized for pulling and grasping, rather than striking or digging. The joint mechanics show adaptations that would have allowed these creatures to hook onto objects and draw them toward their bodies with considerable force. This pulling motion appears to have been their primary feeding strategy, using their massive claws as grappling hooks to bring high vegetation within reach of their mouths. Imagine watching one of these creatures feed. It would approach a tall tree or large shrub and extend its long neck to assess the available food options. Then, rather than trying to reach the highest branches with its mouth, it would deploy its massive claws like living grappling hooks, snagging branches and pulling them down to a height where they could be processed more easily by its beak. This feeding strategy would have given these creatures access to food resources that were completely unavailable to other herbivores of their size. While conventional browsers were limited to vegetation within direct reach of their mouth, these claw-equipped giants could harvest leaves and fruits from much greater heights, effectively expanding their ecological niche into three-dimensional space. The efficiency of this feeding method would have been remarkable. Rather than having to compete directly with other large herbivores for ground-level vegetation, these creatures were exploiting an entirely different layer of the forest ecosystem. They were essentially living as terrestrial giraffes, using mechanical assistance rather than extreme neck elongation to access elevated food sources. But the most fascinating aspect of their feeding behavior becomes apparent when we examine the wear patterns on their fossilized claws. The scratches and stress marks tell a story of incredibly precise and controlled movements. These weren't crude grappling actions, but rather delicate manipulations that required extraordinary coordination between their sensory systems and their muscular control. Evidence suggests that these creatures could identify individual branches or even specific clusters of leaves from considerable distances, then execute pinpoint accurate claw strikes that would secure exactly the vegetation they wanted without damaging surrounding plant material. This level of precision would have required remarkable visual acuity and spatial reasoning abilities that challenge our assumptions about dinosaur intelligence. the cognitive demands of their feeding strategy would have been substantial. These creatures needed to constantly evaluate the structural integrity of potential food sources, calculating whether a particular branch could support the forces they were about to apply, and determining the optimal angle and force for each claw deployment. A miscalculation could result in damaged claws, lost feeding opportunities, or even serious injury from falling debris. This need for constant decision-making and precision control appears to have driven the evolution of enhanced brain structures in these creatures. Fossil skull analysis reveals enlarged regions associated with motor control and spatial processing, suggesting that their nervous systems were specifically adapted for the complex cognitive tasks required by their unique feeding strategy. The social implications of their feeding behavior are equally fascinating. Fossil evidence suggests that these creatures often fed in groups, with multiple individuals working the same general area but targeting different vertical zones within the forest canopy. This coordinated foraging would have maximized the efficiency of their feeding while minimizing direct competition between group members. Some fossil sites preserve evidence of what appears to be cooperative feeding behaviors, with larger individuals using their greater reach to access the highest branches while smaller members of the group focused on intermediate levels. This division of labor would have allowed groups to more thoroughly exploit available food resources while maintaining social cohesion. The seasonal aspects of their feeding strategy add another layer of complexity to their story. Evidence from growth rings in fossilized wood from their environments suggests that these creatures were living in regions with distinct wet and dry seasons. During periods of abundant vegetation, they could afford to be selective, targeting only the most nutritious plant parts. But during dry seasons, their ability to access elevated food sources would have provided crucial survival advantages. Coprolite analysis reveals that these creatures were remarkably flexible in their dietary choices. While they clearly preferred certain types of vegetation, they were capable of processing a wide variety of plant materials when their preferred foods were unavailable. This dietary flexibility, combined with their unique feeding capabilities, would have made them incredibly resilient to environmental changes. The reproductive strategies of these creatures appear to have been closely tied to their feeding ecology. Fossil nesting sites suggest that they constructed their breeding areas in locations that provided optimal access to high-quality vegetation for feeding growing offspring. The positioning of these sites indicates sophisticated planning and site selection that took into account both immediate feeding opportunities and long-term resource availability. Evidence for parental care is particularly compelling in these species. Some fossil sites preserve adult and juvenile specimens in close association, with wear patterns on adult claws suggesting they were using their appendages to process food for their offspring. This food preparation behavior would have been crucial for providing growing juveniles with the high-energy nutrition needed to develop their own specialized anatomy. The development of their distinctive feeding apparatus appears to have been a gradual process that occurred throughout their growth period. Juvenile specimens show progressively increasing claw size and changing joint mechanics as they matured, suggesting that the transition to specialized feeding behavior was accompanied by continuous anatomical refinement. Growth rate analysis indicates that these creatures invested heavily in the development of their feeding apparatus, with claw growth rates that exceeded those of other skeletal elements during certain developmental phases. This preferential investment in their primary feeding tools demonstrates the crucial importance of these structures for their survival and success. The environmental impact of their feeding activities would have been substantial. By selectively harvesting vegetation from elevated positions, these creatures were essentially acting as ecosystem engineers, influencing the structure and composition of forest communities in ways that would have affected numerous other species. Their selective browsing appears to have promoted the growth of certain plant species while suppressing others, creating mosaic landscapes with distinctive vegetation patterns that can still be detected in the fossil record. This ecosystem modification would have created new ecological opportunities for other species while potentially eliminating habitat for others. The evolutionary pressures that shape these creatures extended beyond simple feeding efficiency. Their distinctive anatomy appears to have been influenced by the need to avoid competition with other large herbivores, while exploiting resources that were abundant but difficult to access. This niche partitioning strategy allowed multiple large herbivore species to coexist in the same environments by specializing on different components of the available food resources. The success of this strategy is evident in their widespread distribution and long evolutionary persistence. Fossil evidence shows that these creatures maintained stable populations across multiple continents for millions of years, adapting to a variety of environmental conditions while alizations. Climate change events that caused the extinction of many other large herbivore species appear to have retaining their basic anatomical and ecological special to access elevated food sources may have provided them with crucial and relatively little impact on these creatures. Their ability buffering against environmental changes that reduced ground-level vegetation availability. The defensive aspects of their anatomy add another dimension to their story. While their claws were primarily adapted for feeding, they retained sufficient robustness to serve as formidable weapons when necessary. Evidence from some specimens suggests that these appendages were occasionally used in intraspecific combat, probably during territorial disputes or mating competitions. The positioning and mechanics of their claws would have made them effective defensive weapons against most predators. Their ability to deliver powerful pulling and grasping actions could have been devastating against attackers that ventured within range of their arms. The psychological impact of facing a creature equipped with such impressive appendages would have provided additional protection through intimidation. But perhaps the most remarkable aspect of these creatures is how they demonstrate the incredible versatility of the basic claw design. The same fundamental anatomical structure that we've seen adapted for precision hunting, intimidation display, and specialized digging was here modified for an entirely different purpose, mechanical food processing, and harvesting. This versatility speaks to the remarkable evolutionary potential contained within relatively simple anatomical structures. Through gradual modification of joint mechanics, muscle attachments, and bone proportions, evolution was able to create feeding tools that were perfectly adapted for exploiting previously inaccessible ecological niches. The engineering principles underlying their feeding apparatus are remarkably sophisticated. The leverage ratios of their arm and claw systems were precisely calibrated to deliver optimal force and control for their specific feeding tasks. Minor adjustments to these ratios could have resulted in systems that were either too weak to be effective or so powerful that they were difficult to control. Precisely. Recent biomechanical modeling has revealed just how fine-tuned these systems really were. Computer simulations suggest that their claw mechanics were optimized not just for maximum force delivery, but for energy efficiency and precision control. This optimization would have allowed them to feed for extended periods without excessive fatigue, while maintaining the accuracy needed for selective browsing. The metabolic implications of their feeding strategy were complex. While their specialized anatomy required significant energy investment to develop and maintain, it also provided access to high-quality food sources that could support their metabolic needs more efficiently than conventional browsing strategies. Energy budget analyses suggest that these creatures were able to achieve positive energy balances even during periods of food scarcity, when their ability to access elevated vegetation provided crucial advantages over competitors limited to ground-level resources. This metabolic resilience would have been a key factor in their long-term evolutionary success. The sensory adaptations that accompanied their feeding specializations were equally remarkable. Enhanced depth perception and spatial awareness would have been crucial for accurately targeting branches at various distances and angles. Fossil evidence suggests that their visual systems were specifically adapted for the three-dimensional navigation required by their feeding strategy. Their sense of touch appears to have been highly developed as well, with enlarged nerve pathways that would have provided detailed feedback about the mechanical properties of vegetation they were manipulating. This tactile sensitivity would have allowed them to adjust their grip strength and pulling force in real time to avoid damaging either their food sources or their own claws. The acoustic properties of their feeding activities add another fascinating dimension to their ecology. The sounds produced by their claw-assisted browsing would have been distinctive and probably audible from considerable distances. These feeding sounds may have served as inadvertent communication signals, allowing group members to coordinate their foraging activities or alerting other species to feeding opportunities. Some researchers have suggested that these creatures may have actually evolved to use feeding sounds as intentional communication tools, with different claw manipulation techniques producing distinct acoustic signatures that conveyed information about food quality, feeding site productivity, or potential dangers in the area. The seasonal migration patterns of these creatures appear to have been closely tied to the phenology of their preferred food sources. Evidence suggests that they followed predictable routes that synchronized their movements with the flowering and fruiting cycles of key plant species. This behavioral sophistication demonstrates remarkable ecological awareness and long-term planning abilities. The navigational challenges of maintaining these migration routes would have required sophisticated spatial memory and possibly even transgenerational knowledge transfer. Young animals would have needed to learn complex route information from their parents, creating cultural traditions that were passed down through generations. The archaeological evidence for their presence includes distinctive feeding sign that can be recognized even in the absence of body fossils. Characteristic claw marks on fossilized wood and distinctive patterns of branch breakage provide evidence of their feeding activities across wide geographic areas and extended time periods. These feeding traces are particularly valuable because they provide insights into the behavior and ecology of these creatures that wouldn't be available from skeletal remains alone. The distribution and intensity of feeding sign reveals information about population densities, habitat preferences, and seasonal activity patterns that help us understand how these remarkable creatures lived and thrived in their ancient environments. The preservation of soft tissue impressions in some specimens has provided extraordinary insights into the fine details of their anatomy and behavior. Skin impressions reveal complex patterns of scales and possible proto-feathers that would have provided both protection and thermoregulation. The positioning and orientation of these integumentary structures suggest sophisticated behavioral thermoregulation strategies. Some specimens preserve evidence of specialized skin structures around their claw bases that appear to have been adapted for enhanced sensory feedback during feeding activities. These tactile enhancement structures would have provided detailed information about the mechanical properties of vegetation being manipulated, allowing for even more precise control over their feeding actions. The discovery of fossilized stomach contents has provided direct evidence of their dietary preferences and feeding behaviors. Analysis of these preserved gut contents reveals a remarkably diverse array of plant materials, including leaves, fruits, seeds, and even bark from a wide variety of species. This dietary diversity demonstrates the flexibility and effectiveness of their specialized feeding strategy. Particularly interesting is the evidence for seasonal dietary shifts revealed by specimens preserved at different times of year. During periods of peak vegetation growth, their diet consisted primarily of young leaves and shoots, while during drier seasons they shifted to more fibrous materials including bark and woody stem. This dietary flexibility would have been crucial for surviving in environments with pronounced seasonal variation. The chemical analysis of preserved plant materials from their gut contents has revealed that these creatures were remarkably selective in their feeding choices. Rather than simply consuming whatever vegetation they could access, they appear to have targeted plant parts with optimal nutritional profiles, suggesting sophisticated food recognition and selection abilities. Some of the plant species found in their gut contents are known to contain defensive compounds that would have been toxic to most herbivores. The presence of these materials suggests that these creatures had evolved physiological adaptations that allowed them to process potentially harmful vegetation, further expanding their dietary options and reducing competition with other herbivores. The co-evolutionary relationships between these creatures and their food plants represent one of the most fascinating aspects of their ecology. Evidence suggests that many plant species evolved specific defensive strategies in response to their browsing pressure, while the creatures themselves evolved counter-adaptations that allowed them to continue exploiting these resources. This evolutionary arms race appears to have driven the development of increasingly sophisticated feeding behaviors and anatomical specializations. The precision and selectivity of their feeding activities may have been partly a response to the evolution of plant defenses that required more careful and targeted harvesting strategies. The fossil record preserves evidence of these co-evolutionary dynamics in the form of changing plant morphology and chemistry over time. Species that were heavily browsed by these creatures show evolutionary trends toward increased defensive investment, while the creatures themselves show corresponding improvements in their feeding efficiency and selectivity. The impact of these creatures on plant evolution appears to have extended far beyond their immediate food sources. Their selective browsing activities influenced forest structure and composition in ways that affected the evolutionary trajectories of entire plant communities. This ecosystem-level influence demonstrates the profound ecological importance of their unique feeding strategy. The extinction patterns of these remarkable creatures provide important insights into the factors that determine long-term evolutionary success. Despite their apparent ecological advantages and widespread distribution, most lineages disappeared during major climate change events that occurred toward the end of the Mesozoic era. The timing of their extinction suggests that their specialized feeding strategy, while highly effective under stable conditions, may have made them vulnerable to rapid environmental changes. Their dependence on specific types of vegetation and feeding opportunities may have limited their ability to adapt quickly to changing conditions. However, some lineages appear to have survived these extinction events and continued to evolve into forms that were even more specialized. These surviving groups provide crucial insights into the factors that allowed some specialized species to persist while others disappeared, offering important lessons about evolutionary resilience and adaptation. The legacy of these creatures extends far beyond their direct evolutionary descendants. Their innovative feeding strategies and anatomical adaptations provided evolutionary templates that influenced the development of later herbivorous species. Elements of their feeding ecology can be recognized in various modern animals that have independently evolved similar solutions to comparable ecological challenges. The study of these creatures continues to yield new insights into the principles of evolutionary ecology and adaptation. Their remarkable combination of anatomical specialization and behavioral sophistication demonstrates the incredible potential for evolutionary innovation when organisms are faced with novel ecological challenges and opportunities. Modern analytical techniques are revealing ever more details about their anatomy, behavior, and ecology. Advanced imaging technologies are allowing researchers to study the internal structure of their claws and feeding apparatus with unprecedented resolution, revealing mechanical principles that were previously hidden. Computer modeling of their feeding biomechanics is providing new insights into the efficiency and effectiveness of their strategies. These models are helping researchers understand how minor anatomical modifications could have produced major changes in feeding capability, illuminating the evolutionary pathways that led to their remarkable specializations. The environmental reconstruction of their habitats is becoming increasingly sophisticated as well. Chemical analysis of fossilized soils and plant remains is providing detailed pictures of the ecosystems they inhabited, allowing researchers to understand the ecological context that shaped their evolution and determined their success or failure. These environmental reconstructions are revealing that these creatures lived in remarkably complex ecosystems with high levels of species diversity and intricate ecological interactions. Their specialized feeding strategies were just one component of elaborate food webs that included numerous other specialized species, each adapted to exploit different components of available resources. The discovery of new fossil sites continues to expand our understanding of their geographic distribution and temporal range. Recent finds have revealed that these creatures were even more widespread and diverse than previously recognized, with evidence of their presence on continents and in environments that were previously thought to lack suitable conditions for their survival. These new discoveries are also revealing previously unknown aspects of their anatomy and behavior. Some recently discovered species show feeding adaptations that are even more specialized than anything we've discussed, pushing the boundaries of what we thought was possible in terms of anatomical modification and behavioral specialization. The integration of data from multiple fossil sites is providing insights into population dynamics and social structures that were previously impossible to study. Evidence for herd behavior, migration patterns, and seasonal aggregations is emerging from the careful analysis of multiple fossil localities, revealing complex social and ecological patterns. The implications of this research extend well beyond paleontology into fields ranging from evolutionary biology to ecosystem management. The principles revealed by studying these ancient creatures are informing our understanding of how modern ecosystems function and how they might respond to environmental changes. The conservation applications of this research are particularly important. By understanding how specialized species responded to environmental changes in the past, we can better predict how modern specialists might cope with current and future challenges. The lessons learned from these ancient creatures are helping guide conservation strategies for endangered species that face similar ecological pressures. As we continue to uncover the secrets of these remarkable creatures, their story becomes increasingly relevant to our understanding of life on Earth. They demonstrate that evolution can produce solutions to ecological challenges that seem almost impossibly sophisticated, yet prove to be remarkably effective when viewed from the proper perspective. Their legacy reminds us that the history of life is filled with evolutionary experiments that pushed the boundaries of what seemed possible, creating creatures that were perfectly adapted to their specific ecological niches while contributing to the overall diversity and complexity of life on Earth? The story of these clawed dinosaurs is far from complete, and each new discovery adds another piece to the puzzle of how life adapts and evolves in response to changing environmental conditions. What's clear is that these creatures represent some of the most remarkable examples of evolutionary creativity and ecological adaptation in the fossil record. Their incredible diversity of forms and functions demonstrates that there are countless ways to solve the fundamental challenges of survival and reproduction. From tiny precision hunters to massive intimidation specialists to sophisticated mechanical harvesters, these creatures explored virtually every possible strategy for using claws as survival tools. Yet, even as we celebrate the remarkable achievements of these ancient innovators, we're only beginning to scratch the surface of their true diversity and ecological importance. The next chapter in their story promises to reveal even more extraordinary adaptations and behaviors as we continue to uncover new species and develop better techniques for understanding how these remarkable creatures lived and thrived in their ancient world. But as we prepare to explore the final and perhaps most extraordinary chapter in the story of these clawed dinosaurs, we encounter creatures that took specialization to levels that seem to defy all logic and reason. These weren't just unusual or highly adapted animals. They were evolutionary experiments so extreme that they challenge our fundamental understanding of what's possible in the natural world. We're about to meet the absolute pinnacle of claw evolution, creatures so bizarre that they make everything we've discussed so far look almost conventional by comparison. These were dinosaurs that didn't just push the boundaries of what claws could be used for, they completely redefined what it means to have appendages in the first place. Picture this. You're examining a fossil site, carefully brushing away sediment from what appears to be a relatively normal dinosaur skeleton. The leg bones look familiar. The vertebrae seem typical enough. And then you reach the arms. Suddenly, you're staring at something that looks like it belongs in a science fiction movie rather than the natural world. These aren't just oversized claws or even highly specialized tools. These are structures so massive, so impossibly proportioned, that they seem to violate every principle of practical anatomy. The first time paleontologists encountered these ultimate specialists, they literally didn't know what they were looking at. The sheer scale of the appendages was so far beyond anything in their experience that they couldn't even begin to guess what kind of creature could have produced them. When they finally managed to piece together complete skeletons, the result was so shocking that it forced a complete re-evaluation of what was possible in dinosaur evolution. These creatures had taken the concept of claw specialization to its absolute extreme. We're talking about appendages that were longer than the entire bodies of most dinosaurs, yet were attached to animals that seemed almost comically unsuited to carrying such massive structures. Their bodies had the proportions of living battering rams, built more for absorbing tremendous forces than for the graceful movements you'd expect from creatures equipped with such impressive weaponry. What makes these discoveries so mind-blowing is that biomechanical analysis reveals these massive claws were actually quite fragile. Despite their intimidating appearance, they were constructed more like delicate precision instruments than robust weapons. The internal structure showed hollow chambers and thin walls that would have made them extremely vulnerable to damage if used for anything resembling combat or heavy-duty work. This apparent contradiction between size and strength created one of the most heated debates in paleontological history. How protos happened? Could evolution stages that looked so formidable yet were so obviously impractical for the purposes their appearance suggested? The answer, when it finally emerged, was so unexpected that it revolutionized our understanding of how intimidation and defense strategies work in nature. These creatures had essentially evolved to be living bluffs, developing appendages so visually impressive that they could deter potential threats without ever having to actually use them as weapons. It was a strategy based entirely on psychological warfare, using pure visual impact to avoid physical confrontation that their delicate claws couldn't actually survive. But here's where the story takes an even more fascinating turn. Recent discoveries have revealed that these intimidation specialists weren't just passive creatures hoping to avoid conflict through their impressive appearance. Instead, they had evolved sophisticated behavioral repertoires that maximized the psychological impact of their massive appendages through carefully choreographed threat displays. Trackway evidence shows that these creatures could manipulate their body posture and arm positioning to create threat displays that would have been absolutely terrifying to encounter. They could spread their massive claws to create silhouettes that appeared even larger than their already impressive actual size, while coordinating their movements to create maximum visual impact. The precision required for these threat displays was remarkable. Fossil evidence suggests that these creatures could control the positioning of their massive appendages with extraordinary accuracy, creating displays that were perfectly calibrated to the specific threat they were facing. A display directed at a smaller predator would be subtly different from one aimed at a larger competitor, demonstrating sophisticated abilities, assessment, and behavioral flexibility. The metabolic cost of maintaining such massive appendages would have been enormous. These structures required tremendous amounts of energy to grow and maintain, yet they provided no direct assistance with feeding or locomotion. The fact that evolution favored such seemingly wasteful investments demonstrates just how effective their intimidation strategy must have been. Energy budget calculations reveal that these creatures were essentially investing a huge portion of their metabolic resources in what amounted to biological advertising. Like peacocks with their elaborate tail displays, these dinosaurs were trading practical utility for psychological impact, betting their survival on the effectiveness of their visual deterrent systems. The social implications of their threat display behaviors were equally complex. Evidence suggests that these creatures used their massive claws not just for deterring predators, but also for intraspecific communication and competition. Fossil sites preserve evidence of what appear to be ritualized combat displays between individuals. with specific positioning and movement patterns that suggest highly structured social interactions. These social displays would have been spectacular to witness. Imagine two of these massive creatures facing off against each other, each trying to appear more intimidating than the other through carefully orchestrated movements of their enormous appendages. The psychological intensity of such encounters would have been incredible, with the outcome determined not by physical combat, but by which individual could create the more impressive visual display. The seasonal aspects of their display behaviors add another layer of complexity to their story. Evidence suggests that the intensity and frequency of their threat displays varied throughout the year, possibly in response to breeding cycles or seasonal changes in food availability. During certain periods, these creatures appear to have engaged in almost constant display activities, creating prehistoric landscapes that must have been filled with dramatic visual spectacles. The evolutionary pressures that drove such extreme display specialization must have been absolutely intense. We're talking about selection forces so powerful that they could overcome the obvious disadvantages of carrying such massive, fragile appendages. The predation pressure and competitive dynamics in their ecosystems must have been so severe that even the enormous costs of their intimidation systems were justified by their survival benefits. What makes this even more remarkable is that these extreme display specialists weren't just successful in one particular environment or time period. Fossil evidence shows that similar creatures evolved independently in multiple locations around the world, suggesting that the ecological conditions favoring such strategies were widespread and persistent throughout much of dinosaur history. This global pattern of convergent evolution toward extreme display specialization tells us something profound about the role of psychological warfare in prehistoric ecosystems. The repeated evolution of similar solutions suggests that intimidation through visual display was not just an effective strategy, but virtually inevitable under certain ecological conditions. The technological challenges of studying these creatures have pushed paleontological research techniques to their limits. The sheer size and fragility of their appendages makes them extremely difficult to excavate, transport, and study without damage. Specialized equipment and techniques have had to be developed specifically for handling these massive, delicate structures. Advanced imaging technologies are revealing incredible details about the internal structure of their claws that were previously impossible to study. CT scans and other non-invasive techniques are showing complex internal architectures with hollow chambers, reinforcing struts and weight reduction features that demonstrate sophisticated biological engineering principles. Computer modeling of their threat display mechanics is providing insights into how these creatures could manipulate such massive appendages with the precision required for effective psychological warfare. The biomechanical calculations reveal muscle and joint arrangements that were specifically optimized for display movements rather than practical functions. The acoustic aspects of their displays are also becoming clearer through detailed analysis of their skeletal structure. Evidence suggests that these creatures could produce distinctive sounds by manipulating their massive claws, adding an auditory component to their visual threat displays that would have made them even more intimidating. The environmental impact of their display behaviors would have been substantial. The energy requirements for maintaining their massive appendages and executing their threat displays would have influenced their feeding patterns and habitat selection in ways that affected entire ecosystem dynamics. Their presence in prehistoric communities appears to have created cascading effects throughout food webs. By effectively deterring predation through their intimidation strategies, these creatures may have altered predator behavior patterns in ways that influence the survival and distribution of other species. The coevolutionary arms race between these display specialists and their predators represents one of the most fascinating aspects of their ecology. As these creatures evolved more effective intimidation strategies, their predators appear to have evolved counter-adaptations that allowed them to distinguish between genuine threats and mere displays. Evidence suggests that some predators developed enhanced assessment abilities that allowed them to evaluate the actual threat level posed by these intimidating displays. This predator sophistication would have created additional selection pressure for even more convincing and elaborate display behaviors. The developmental biology of their massive appendages reveals complex growth patterns that required precise coordination between multiple biological systems. The timing and rate of claw growth had to be carefully regulated to ensure that the developing structures remained functional throughout the growth process. Juvenile specimens show dramatically different proportions from adults, suggesting that the transition to full display capability required significant anatomical reorganization as individuals matured. This developmental complexity would have made these creatures particularly vulnerable during their growth period. The parental investment required to successfully raise offspring with such complex developmental requirements would have been enormous. Evidence suggests that these creatures provided extended parental care, protecting and provisioning their young throughout the lengthy period required for their display apparatus to fully develop. The learning component of their display behaviors appears to have been substantial as well. Young individuals would have needed to master the complex motor skills required for effective threat displays, suggesting that behavioral instruction from parents and other group members was crucial for their survival. The cultural transmission of display techniques may have created regional variations in threat behavior patterns. Different populations appear to have developed subtly different display styles, possibly reflecting local adaptation to specific predator communities or environmental conditions. The seasonal migration patterns of these creatures seem to have been influenced by the energetic demands of their display systems. During periods when threat displays were most important, they appear to have concentrated in areas with abundant food resources that could support their high metabolic requirements. The fossil preservation of their massive appendages has created some of the most spectacular museum displays in paleontology. The visual impact of seeing these enormous structures in person helps visitors understand the psychological effect they would have had on other creatures in their ancient ecosystems. However, the display-oriented preservation of these fossils has sometimes led to misunderstandings about their actual function. The impressive appearance of museum mounts can reinforce misconceptions about these structures being weapons rather than display organs, highlighting the ongoing need for public education about their true purpose. The conservation implications of studying these ancient display specialists are particularly relevant in our modern world. Many contemporary species rely on elaborate threat displays for survival, and understanding how these strategies evolved and functioned in the past can inform conservation efforts for species facing similar challenges today. The habitat requirements for supporting creatures with such energetically expensive display systems provide insights into ecosystem health and stability. The presence of extreme display specialists in fossil communities indicates environments that were productive enough to support such metabolically demanding strategies. Climate change effects on these ancient display specialists can be tracked through the fossil record, revealing how environmental changes affected species that were heavily invested in energetically expensive survival strategies. These patterns provide important models for predicting how modern display specialists might respond to current environmental changes. The extinction patterns of these creatures reveal important information about the vulnerability of highly specialized species to environmental change. Despite their apparent success at deterring predators, their extreme specialization appears to have made them particularly vulnerable to ecosystem disruptions. The timing of their extinction events suggests that rapid environmental changes could disrupt the ecological conditions that made their expensive display strategies viable. When systems became able, the energetic costs of maintaining their massive appendages may have outweighed their survival benefits. However, some lineages appear to have survived by reducing their investment in display structures and developing more practical appendage functions. These evolutionary transitions provide fascinating examples of how extreme specialists can sometimes adapt to changing conditions by abandoning their specializations. The legacy of these ultimate display specialists extends far beyond their direct evolutionary descendants. Their innovative approaches to threat deterrence and psychological warfare provided evolutionary templates that influenced the development of display behaviors in numerous other lineages. Modern examples of similar strategies can be found throughout the animal kingdom, from the elaborate threat displays of modern birds to the intimidation behaviors of various mammals. The principles pioneered by these ancient creatures continue to influence how animals use visual communication for survival. The biomechanical innovations required for their display systems have also inspired technological applications. Engineers studying their appendage mechanics have developed new approaches to creating lightweight yet visually impressive structures for various industrial applications. The psychological principles underlying their intimidation strategies have informed research in fields ranging from animal behavior to human psychology. Understanding how these creatures use visual cues to influence the behavior of other animals provides insights into the fundamental mechanisms of threat assessment and decision-making. The artistic and cultural impact of these creatures has been substantial as well. Their dramatic appearance and fascinating behavioral ecology have captured public imagination in ways that have helped promote interest in paleontology and evolutionary biology. Popular media representations of these creatures have generally focused on their impressive visual appearance while often misrepresenting their actual function. This has created both opportunities and challenges for science education, as their dramatic appearance attracts attention but can also perpetuate the ongoing weight misconceptions. Discovery of new species and new fossil sites continues to expand our understanding of these remarkable creatures. Recent finds have revealed even more extreme examples of display specialization, with some species showing appendage proportions that push the boundaries of what seems physically possible. Advanced analytical techniques are revealing previously hidden aspects of their biology and behavior. Chemical analysis of fossilized tissues is providing new insights into their physiology and metabolism, while detailed biomechanical modeling is illuminating the precise mechanics of their threat display behaviors. The integration of data from multiple research approaches is creating increasingly sophisticated models of how these creatures lived and functioned in their ancient ecosystems. This multidisciplinary approach is revealing complexity and sophistication that was previously unimaginable. The implications of this research extend well beyond our understanding of these particular creatures. They demonstrate that evolution can produce solutions to survival challenges that seem almost impossibly specialized, yet prove to be remarkably effective when viewed from the proper ecological perspective. Their story reminds us that the history of life is filled with evolutionary experiments that explored every possible strategy for survival and reproduction. From precision hunting tools to massive intimidation displays to sophisticated mechanical harvesters, these clawed dinosaurs represent just a small sample of the incredible diversity of solutions that evolution has produced. The continued study of these remarkable creatures promises to yield even more insights into the principles of evolutionary adaptation and ecological specialization. Each new discovery adds another piece to the puzzle of how life adapts to changing environmental conditions and exploits new ecological opportunities. As we look toward the future of paleontological research, these clawed dinosaurs will undoubtedly continue to surprise and amaze us with their innovations and adaptations. Their legacy serves as a testament to the incredible creativity of evolutionary processes and the remarkable diversity of life that has existed on our planet. The story of these bizarre appendages ultimately teaches us that there are no limits to the creative solutions that evolution can produce when organisms face survival challenges. From the smallest precision hunters to the largest intimidation specialists, these creatures explored virtually every possible way to use claws as tools for survival and success. Their incredible diversity reminds us that life finds a way to exploit every available ecological niche, often through strategies that seem completely counterintuitive from a human perspective. The success of creatures with seemingly impractical appendages demonstrates that evolution operates by different rules than human engineering, often producing solutions that work perfectly despite appearing impossible. The technological marvels represented by their specialized appendages continue to inspire new research and innovation across multiple fields. From biomechanics to material science to robotics, the principles revealed by studying these ancient creatures are informing the development of new technologies and approaches to engineering challenges. Perhaps most importantly, these creatures remind us of the incredible privilege we have in being able to study and understand the history of life on Earth. Through careful scientific investigation, we can reconstruct the lives and behaviors of creatures that lived millions of years ago, gaining insights now into evolutionary processes that shape the world we inhabit today. The story of these clawed dinosaurs is far from over. As new fossils are discovered and new analytical techniques are developed, we will undoubtedly uncover even more remarkable examples of evolutionary innovation and adaptation. Each new discovery will add another chapter to the incredible story of how life has adapted and evolved over hundreds of millions of years. The legacy of these creatures extends into our modern world through their influence on evolutionary biology, conservation science, and our understanding of ecological relationships. Their remarkable adaptations continue to inform our efforts to understand and protect the biodiversity that surrounds us today. As we face our own environmental challenges and work to preserve the incredible diversity of life on Earth, the lessons learned from these ancient innovators become increasingly relevant. Their story demonstrates that life is remarkably resilient and creative, capable of finding solutions to even the most challenging survival problems. The continued fascination with these creatures among scientists and the public alike ensures that their story will continue to be told and retold, inspiring new generations of researchers and conservationists. Their incredible diversity and remarkable adaptations serve as powerful reminders of the wonder and complexity of the natural world. In the end, these clawed dinosaurs represent some of the most extraordinary examples of evolutionary creativity in the history of life on Earth. Their bizarre appendages and specialized behaviors demonstrate that there are no limits to the innovative solutions that evolution can produce when organisms are faced with survival challenges. Their story is a celebration of the incredible diversity of life and a testament to the power of scientific investigation to reveal the secrets of our planet's remarkable biological heritage. Through continued research and discovery, we will undoubtedly uncover even more amazing examples of evolutionary innovation, adding new chapters to the ever-expanding story of life on Earth. The incredible journey through the world of these clawed dinosaurs has revealed creatures so diverse, so specialized, and so remarkably adapted to their specific ecological niches that they challenge our fundamental assumptions about what's possible in the natural world. From tiny precision hunters to massive intimidation specialists, these remarkable animals virtually explore every conceivable strategy for using claws as survival tools. Their legacy continues to influence our understanding of evolution, ecology, and the incredible potential for life to adapt and innovate in response to environmental challenges. As we continue to study these fascinating creatures, we gain deeper insights into the processes that have shaped the diversity of life on our planet and the remarkable creativity of evolutionary adaptation. The story of these bizarre clawed dinosaurs is ultimately a story about the limitless potential of life itself, demonstrating that given enough time and selective pressure, evolution can produce solutions that seem almost magical in their sophistication and effectiveness. Their remarkable achievements serve as inspiration for our continued efforts to understand and appreciate the incredible diversity of life that has existed on Earth throughout its long and fascinating history. The quest to understand these remarkable creatures takes yet another extraordinary turn when we delve into the fossil record of North America, where paleontologists uncovered evidence of some of the smallest yet most perfectly adapted claw specialists ever discovered. These weren't the massive intimidation displays we just explored, nor were they the precision instruments of their Asian cousins. Instead, these North American discoveries revealed creatures that had achieved something truly remarkable. They had managed to compress all the sophistication and specialization we've seen in larger forms into packages so compact they could literally fit in your backpack. Picture discovering a dinosaur skeleton that measures barely 3 feet from nose to tail, yet possesses claws that are proportionally larger than those of a grizzly bear. The initial reaction of researchers to these finds was one of complete bewilderment. How could such tiny creatures justify the metabolic investment required to grow and maintain such impressive appendages? The answer, when it finally emerged through years of careful analysis, revealed one of the most elegant solutions to survival challenges ever documented in the fossil record. These diminutive specialists had essentially become the Swiss Army knives of the dinosaur world. Their oversized claws weren't just single-purpose tools, but rather multifunctional implements that could serve as excavation equipment, precision manipulators, defensive weapons, and even communication devices, all rolled into one incredibly efficient package. The engineering principles underlying their design were so sophisticated that modern robotics engineers study their joint mechanics for inspiration in creating versatile mechanical systems. What makes these discoveries so remarkable is the evidence for their incredible diversity within such a constrained body plan. Despite their similar small sizes, different species had evolved claws with dramatically different shapes, proportions, and apparent functions. Some possessed straight pointed talons that were clearly optimized for probing and piercing activities. Others had developed curved, hook-like appendages that seemed designed for grasping and manipulating objects with extraordinary precision. The most fascinating aspect of these tiny specialists was their apparent ability to modify their behavior and claw usage based on seasonal changes and resource availability. Wear pattern analysis reveals that individual animals were using their claws for different purposes at different times of the year, switching between digging activities during certain seasons and more delicate manipulation tasks during others. This behavioral flexibility would have provided crucial survival advantages in environments where resource availability fluctuated dramatically throughout the year. The social implications of their compact size and specialized tools created entirely new ecological dynamics that hadn't been seen in their larger relatives. Evidence suggests that these tiny creatures could work cooperatively in ways that would have been impossible for bigger species. Fossil sites preserved trackways showing multiple individuals apparently coordinating their excavation activities, creating collective digging projects that could access resources far beyond what any single animal could reach. This cooperative behavior appears to have extended to their reproductive strategies as well. Nesting sites show evidence of communal child-rearing activities, with multiple adults apparently sharing responsibility for protecting and provisioning young animals. The compact size of these creatures would have made such cooperative breeding systems much more practical than they would have been for larger species. The predation pressures facing these small specialists created fascinating evolutionary responses that pushed the boundaries of what seemed possible in terms of defensive strategies. Despite their tiny size, these creatures had evolved remarkably sophisticated escape and evasion techniques that took full advantage of their specialized anatomy. Their powerful claws could be used to rapidly excavate emergency shelters, while their compact proportions allowed them to access hiding places that would have been unavailable to larger animals. Some species appear to have developed truly extraordinary defensive behaviors that combine their digging abilities with remarkable tactical intelligence. Evidence suggests that certain forms could create complex burrow systems with multiple entrances and emergency exits, essentially building underground fortresses that provided protection from even the most persistent predators. The metabolic challenges of maintaining such proportionally large claws in such small bodies drove the evolution of some of the most efficient physiological systems ever documented in dinosaurs. These creatures had to extract maximum energy from every food item they consumed, leading to digestive systems that were incredibly effective at processing high-quality nutrition from relatively small quantities of food. Their hunting strategies reflected this need for maximum efficiency. Rather than pursuing large prey items that might provide substantial energy but require significant expenditure to capture, these specialists focused on small energy-dense targets that could be acquired with minimal effort. Their preferred prey appears to have consisted primarily of insect larvae, small vertebrates, and other concentrated protein sources that provided optimal energy returns for their hunting investments. The sensory adaptations required for such precise hunting in compact packages led to some truly remarkable evolutionary innovations. These tiny predators had developed sensory systems that were proportionally more sophisticated than those of much larger animals. Their ability to detect minute vibrations, chemical traces, and acoustic signals allowed them to locate hidden prey with extraordinary accuracy. Most remarkably, some species appear to have evolved echolocation capabilities that rivaled those of modern bats. The bone structure around their inner ears shows adaptations consistent with both the production and reception of high-frequency sound waves, suggesting they could navigate and hunt effectively even in complete darkness or in complex underground environments where visual hunting would have been impossible. These acoustic hunting abilities would have opened up entirely new ecological niches that were inaccessible to other predators. By hunting in darkness and in confined spaces, these creatures could exploit prey populations that were essentially invisible to conventional predators. This gave them access to resources that could support their populations, even when larger predators were experiencing food shortages. The technological challenges of studying creatures this small has pushed paleontological research techniques into entirely new territories. Traditional excavation and analysis methods designed for larger specimens simply don't work when dealing with fossils that are measured in centimeters rather than meters. Specialized micro-excavation techniques and high-resolution imaging systems have had to be developed specifically for studying these tiny specialists. Advanced microscopy techniques are revealing details about their anatomy that would have been completely invisible using conventional analysis methods. The internal structure of their miniaturized claws shows engineering principles that operate at scales where traditional mechanical concepts begin to break down and surface forces become more important than bulk material properties. Computer modeling of their biomechanics requires entirely different approaches than those used for larger animals. At their scale, factors like surface tension, air resistance, and thermal regulation become much more significant, creating design constraints that simply don't apply to bigger creatures. Understanding how these tiny specialists solve these challenges is providing insights that are applicable to fields ranging from micro-robotics to nanotechnology. The preservation quality of these small fossils has provided unprecedented insights into soft tissue structures that are rarely preserved in larger specimens. The fine-grained sediments that typically preserve such tiny remains have captured details of skin texture, possible feather structures, and even internal organ arrangements that give us remarkably complete pictures of how these creatures appeared and functioned in life. Some specimens preserve evidence of complex integumentary structures that appear to have served multiple functions simultaneously. Possible proto-feathers show adaptations for thermoregulation, sensory enhancement, and even acoustic modification that would have improved their echolocation abilities. The multifunctional nature of these structures demonstrates the efficiency pressures that drove their evolution. The color patterns preserved in some specimens reveal that despite their small size, these creatures invested significantly in visual communication systems. Some species show evidence of remarkably bright and complex coloration patterns that would have been easily visible to other members of their species, even in the low-light conditions where they typically operated. The seasonal aspects of their coloration appear to have been particularly sophisticated. Evidence suggests that some species could actually change their color patterns in response to environmental conditions or social situations, providing them with dynamic camouflage and communication capabilities that enhanced both their hunting success and their survival prospects. The reproductive strategies of these tiny specialists required solutions to challenges that simply didn't exist for larger animals. The energy investment required for egg production represented a much more significant portion of their total metabolic budget, forcing the evolution of remarkably efficient reproductive systems that maximize the chances of successful offspring production. Evidence suggests that some species had evolved remarkably sophisticated parental care behaviors that ensured their tiny offspring received optimal nutrition and protection during their vulnerable early development. The precision required for caring for such small young would have demanded extraordinary behavioral sophistication and coordination between parents. The developmental biology of these creatures reveals growth patterns that were precisely calibrated to maintain optimal proportions throughout their life cycle. The timing of claw development had to be carefully coordinated with overall body growth to ensure that individuals remained functional at every stage of their development. Juvenile specimens show that young animals possessed proportionally different anatomy than adults, suggesting that they exploited different ecological niches during their growth period. This ontogenetic niche shifting would have reduced competition between different age classes, while ensuring that resources were used as efficiently as possible throughout their life cycle. The migration patterns of these tiny specialists created some of the most complex movement dynamics ever documented in dinosaur populations. Their small size allowed them to exploit transportation opportunities that would have been unavailable to larger animals. Evidence suggests that some species may have actually used larger dinosaurs as inadvertent transportation systems, traveling significant distances by hitching rides on their massive contemporaries. This commensalistic relationship would have provided these tiny creatures with access to feeding opportunities across vast geographic ranges while minimizing their own energy expenditure for long-distance travel. The behavioral sophistication required to successfully exploit such opportunities demonstrates remarkable intelligence and adaptability. The fossil record preserves evidence of truly extraordinary population densities for these creatures in certain locations and time periods. Some fossil sites contain hundreds of individual specimens in relatively small areas, suggesting that these tiny specialists could achieve population concentrations that would have been impossible for larger animals. These high-density populations appear to have created complex social dynamics that included sophisticated communication systems, resource-sharing behaviors, and coordinated responses to environmental challenges. The ability to maintain such dense populations while avoiding destructive competition demonstrates remarkable social and ecological sophistication. The environmental impact of these dense populations would have been substantial despite the small size of individual animals. Their collective excavation activities could significantly modify soil structure and composition, while their predation pressure on insect and small vertebrate populations would have had cascading effects throughout entire ecosystem food webs. The coevolutionary relationships between these tiny predators and their prey communities represent some of the most intricate ecological interactions documented in the fossil record. The precision and efficiency of their hunting strategies appears to have driven corresponding evolutionary responses in their prey species, creating arms races that operated at microscopic scales. Evidence suggests that some prey species evolved increasingly sophisticated concealment and defensive strategies in response to predation pressure from these tiny specialists. The fossil record preserves examples of prey animals with enhanced burrowing abilities, chemical defenses, and even possible cooperative anti-predator behaviors that were specifically adapted to counter the hunting strategies of these small predators. The extinction patterns of these tiny specialists provide crucial insights into the factors that determine survival during major environmental changes. Despite their apparent advantages in terms of efficiency and adaptability, many lineages disappeared during the same extinction events that eliminated their larger relatives. The vulnerability of these highly specialized creatures to environmental change appears to have been related to their dependence on very specific ecological conditions that supported their unique lifestyle. When these conditions changed, their extreme specializations became disadvantages that prevented them from adapting to new circumstances. However, some lineages appear to have survived by maintaining greater behavioral flexibility and less extreme anatomical specializations. These surviving groups provide important examples of how evolutionary compromises between specialization and generalization can determine long-term survival prospects. The legacy of these tiny specialists extends far beyond their direct evolutionary influence. Their innovations in miniaturization and efficiency have inspired research in fields ranging from engineering to medicine. Understanding how they solved the challenges of maintaining complex functionality in extremely small packages provides insights that are applicable to numerous technological applications. Modern examples of similar miniaturization strategies can be found throughout the natural world, from the smallest mammals to various arthropod species. The principles pioneered by these ancient creatures continue to influence how organisms solve the challenges of surviving and thriving in resource-limited environments. The conservation implications of studying these ancient miniature specialists are particularly relevant for understanding how small, specialized species respond to environmental changes. Many modern ecosystems contain species that face similar challenges to those encountered by these prehistoric creatures, and understanding their strategies and limitations provides valuable guidance for conservation efforts. The habitat requirements for supporting such highly specialized small predators reveal important information about ecosystem health and stability. The presence of these creatures in fossil communities indicates environments that were sufficiently stable and productive to support such metabolically demanding specializations over extended time periods. As we continue to discover new species and develop better analytical techniques for studying these remarkable creatures, our understanding of their biology and ecology continues to expand and evolve. Recent discoveries have revealed even more extreme examples of miniaturization and specialization, pushing the boundaries of what we thought was possible in terms of scaling biological systems. down to incredibly small sizes, the integration of data from multiple fossil sites and analytical approaches is creating increasingly sophisticated models of how these tiny specialists functioned within their ancient ecosystems. This multidisciplinary research is revealing complexity and sophistication that rivals anything seen in modern ecosystems, demonstrating that size is no barrier to evolutionary innovation and ecological success. The story of these miniature marvels ultimately demonstrates that evolution can produce effective solutions to survival challenges, regardless of the scale at which those challenges must be addressed, from the largest intimidation displays to the smallest precision instruments. The diversity of claw specializations we've explored represents just a fraction of the incredible creativity and adaptability that characterizes life on Earth. Their remarkable achievements serve as powerful reminders that evolutionary success isn't determined by size, strength, or conventional advantages, but rather by the ability to find and exploit ecological opportunities through innovative adaptations and behaviors. These tiny specialists achieved extraordinary success by perfecting strategies that were perfectly matched to their specific environmental circumstances and ecological requirements. The continued study of these fascinating creatures promises to yield even more insights into the principles that govern evolutionary miniaturization and specialization. Each new discovery adds another piece to our understanding of how life adapts to extreme constraints and finds ways to thrive even under the most challenging circumstances. As we look toward the future of research on these remarkable animals, we can expect to uncover even more examples of their incredible innovations and adaptations. Their story serves as inspiration for our continued efforts to understand the full scope of evolutionary creativity and the remarkable diversity of solutions that life has developed for surviving and prospering in an ever-changing world. The legacy of these clawed dinosaurs, from the largest to the smallest, from the most intimidating to the most precise, ultimately teaches us that there are no limits to the creative potential of evolutionary processes. Their incredible diversity and remarkable specializations demonstrate that given sufficient time and selective pressure, life can find ways to exploit virtually any conceivable ecological opportunity. Their story is a celebration of the ingenuity and adaptability that characterizes life itself, reminding us that the natural world is filled with solutions to challenges that seem impossible from our limited human perspective. Through continued scientific investigation and discovery, we will undoubtedly uncover even more examples of evolutionary innovation, adding new chapters to the ever-expanding story of life's remarkable creativity and resilience. The most extraordinary chapter in our clawed dinosaur saga unfolds when we encounter creatures that represent the absolute pinnacle of evolutionary audacity. We're talking about dinosaurs that didn't just modify their appendages. They completely revolutionized what it means to be a herbivore in a world dominated by apex predators. Picture walking through an ancient forest and coming face to face with a creature that defies every assumption you've ever had about plant eaters. This isn't some gentle, defenseless browser cowering from predators. Instead, you're staring at what appears to be a walking fortress equipped with the most intimidating weaponry you've ever seen. Yet this apparent killing machine is peacefully munching on leaves like the world's most overbuilt lawnmower. These creatures had taken the evolutionary gamble of a lifetime. Instead of developing speed, armor, or herd behavior for protection, they had invested everything in psychological warfare. Their claws weren't just large, they were absolutely colossal, reaching lengths that would make a medieval sword look like a toothpick. Some specimens preserve evidence of individual claws that stretched over half a meter in length, creating appendages so visually striking that they would have dominated the entire appearance of these already massive animals. But here's where this story takes its most mind-bending turn. Despite their fearsome appearance, biomechanical analysis reveals that these enormous claws were actually quite delicate structures. The internal architecture shows hollow chambers and thin walls that would have made them extremely vulnerable to the stresses of actual combat. These weren't weapons at all. They were the most elaborate bluffs in the history of life on Earth. The genius of their strategy becomes apparent when you consider the predators they were facing. We're talking about ecosystems populated by some of the most formidable carnivores ever to walk the planet. Massive theropods with bone-crushing jaws and lightning reflexes prowled these ancient landscapes, constantly searching for their next meal. In this environment, even a moment's hesitation from a predator could mean the difference between becoming dinner and living to see another day. These herbivorous giants had essentially weaponized pure intimidation. Their massive claws created such a powerful visual impact that most predators would think twice before attacking, even if they somehow knew that the impressive appendages weren't particularly effective as actual weapons. It was evolutionary theater on the grandest possible scale, with survival depending entirely on the quality of the performance. The behavioral repertoires that accompanied these intimidation displays were remarkably sophisticated. Fossil trackways preserved evidence of threat postures and movement patterns that suggest these creatures could orchestrate truly spectacular defensive displays. They could spread their massive claws to create silhouettes that appeared even larger than their already impressive actual dimensions, while coordinating their body movements to maximize the psychological impact of their performance. Recent discoveries have revealed that different species had evolved subtly different display strategies, suggesting that they were specifically adapted to deter different types of predators. Some forms appear to have specialized in creating displays that were particularly effective against larger carnivores, while others had developed techniques that were better suited for discouraging smaller, more agile predators. The metabolic cost of maintaining such enormous appendages was absolutely staggering. These structures required tremendous amounts of energy to grow and maintain, yet they provided no assistance whatsoever with feeding or locomotion. The fact that natural selection favored such seemingly wasteful investments demonstrates just how effective their intimidation strategy must have been in practice. Energy budget calculations reveal that these creatures were essentially investing the equivalent of a small car's worth of calories into what amounted to biological advertising. Like a company spending enormous sums on marketing, these dinosaurs were trading immediate practical benefits for long-term survival advantages through reputation management and deterrent effects. The engineering challenges of supporting such massive appendages while maintaining mobility created some fascinating anatomical innovations. Their shoulder girdles had evolved into incredibly robust anchor points that could distribute the tremendous forces generated by their oversized claws. The muscle arrangements required to control these appendages represented some of the most sophisticated biomechanical systems ever documented in the fossil record. What makes their story even more remarkable is the evidence for seasonal variation in their display behaviors. Fossil sites preserve specimens that appear to have been preserved during different times of the year, revealing that the intensity and frequency of their threat displays varied considerably based on environmental conditions and, presumably, predation pressure. During certain seasons, these creatures appear to have engaged in almost constant display activities, creating prehistoric landscapes that must have been filled with dramatic visual spectacles, as massive herbivores repeatedly demonstrated their apparent fighting prowess to any potential threats in the vicinity. The social dynamics created by their intimidation strategies added yet another layer of complexity to their already fascinating ecology. Evidence suggests that these creatures lived in loose aggregations that provided mutual support for their defensive displays. Multiple individuals displaying simultaneously would have created an absolutely overwhelming visual impact that few predators would have been willing to challenge. Some fossil sites preserve evidence of what appear to be coordinated group displays, with multiple animals apparently synchronizing their threat behaviors to create maximum psychological impact. The coordination required for such group performances suggests remarkably sophisticated communication systems and social awareness. The evolutionary arms race between these intimidation specialists and their predators represents one of the most fascinating co-evolutionary dynamics documented in the fossil record. As these herbivores developed more convincing threat displays, their predators appear to have evolved enhanced assessment abilities that allowed them to distinguish between genuine dangers and mere theatrical performances. Evidence suggests that some carnivores developed behavioral strategies specifically designed to test the resolve of these intimidating herbivores. Fossil trackways preserve what appear to be stalking patterns where predators approached these creatures in ways that would force them to either back up their impressive displays with actual combat or reveal the limitations of their defensive strategy. This predator sophistication created additional evolutionary pressure for even more elaborate and convincing display behaviors. The creatures that survived were those that could maintain the most believable performance under the most challenging circumstances, leading to an escalating cycle of theatrical innovation and assessment sophistication. The developmental biology of their massive claws reveals growth patterns that required extraordinary precision and coordination. The timing and rate of claw development had to be carefully calibrated to ensure that the structures remained proportional and functional throughout the animal's growth period. A slight miscalculation in growth rates could have resulted in appendages that were either too small to be intimidating or too large to be manageable. Juvenile specimens show dramatically different proportions from adults, indicating that the transition to full intimidation capability required significant anatomical reorganization as individuals matured. Young animals appear to have relied on different defensive strategies, possibly including speed and concealment, before developing the massive appendages that would define their adult lifestyle. The parental investment required to successfully raise offspring with such complex developmental requirements would have been enormous. Parents would have needed to protect and provision their vulnerable young throughout the extended period required for their intimidation apparatus to fully develop and become effective. The learning component of effective threat display appears to have been substantial as well. Young individuals would have needed to master the complex motor skills and behavioral timing required to execute convincing displays. This suggests that cultural transmission of display techniques from parents and other group members was crucial for survival. Regional variations in display styles preserved in different fossil localities suggest that these cultural learning processes created distinct behavioral traditions in different populations. Some regions appear to have developed more aggressive display styles, while others favored more subtle intimidation approaches, possibly reflecting adaptation to different local predator communities. The habitat requirements for supporting creatures with such energetically expensive defensive strategies provide important insights into prehistoric ecosystem productivity and stability. The presence of these intimidation specialists in fossil communities indicates environments that were sufficiently productive to support the enormous metabolic investments required for their survival strategy. Climate analysis reveals that these creatures were most successful in regions with stable, warm climates that supported high plant productivity throughout the year. The energy demands of their massive appendages would have made them particularly vulnerable to environmental conditions that reduced food availability or increased the costs of foraging. The extinction patterns of these remarkable creatures provide sobering lessons about the vulnerability of highly specialized species to environmental change. Despite their apparent success at deterring predators, their extreme investment in intimidation displays appears to have made them particularly susceptible to ecosystem disruptions that altered the fundamental conditions supporting their survival strategy. When rapid climate changes reduced plant productivity or altered predator-prey dynamics, the enormous costs of maintaining their defensive displays may have suddenly outweighed their survival benefits. The creatures that had invested most heavily in intimidation were often the first to disappear when environmental conditions changed. However, some lineages appear to have survived these challenges by gradually reducing their investment in display structures and developing more practical uses for their appendages. These evolutionary transitions represent fascinating examples of how extreme specialists can sometimes adapt to changing conditions by abandoning their most distinctive specializations. The legacy of these ultimate intimidation specialists extends far beyond paleontology into fields ranging from evolutionary psychology to military strategy. Their sophisticated understanding of threat assessment and deterrent effectiveness provides insights into fundamental principles that continue to influence behavior and decision-making across the natural world. Modern examples of similar intimidation strategies can be found throughout contemporary ecosystems, from the threat displays of various birds to the defensive posturing of numerous mammalian species. The psychological principles pioneered by these ancient creatures continue to shape how animals use visual communication and behavioral performance for survival. The biomechanical innovations required for their display systems have inspired technological applications in fields ranging from robotics to architectural engineering. Understanding how these creatures manage to create maximum visual impact while minimizing structural weight has informed the development of lightweight yet impressive structures for various industrial purposes. As we continue to uncover new fossil evidence and develop more sophisticated analytical techniques, our understanding of these remarkable creatures continues to evolve and expand. Recent discoveries have revealed species with even more extreme display adaptations, pushing the boundaries of what seemed possible in terms of intimidation specialization. The story of these clawed giants ultimately demonstrates that evolution can produce solutions to survival challenges that seem almost impossibly creative, yet prove remarkably effective when viewed from the proper ecological perspective. Their success through pure psychological warfare represents one of the most innovative survival strategies ever documented in the fossil record. Their incredible achievements remind us that the history of life is filled with evolutionary experiments that explored every conceivable approach to the fundamental challenges of survival and reproduction. From precision hunting tools to massive intimidation displays, these creatures represent just a small sample of the extraordinary diversity of solutions that natural selection has produced over millions of years of Earth's history. The continued study of these fascinating animals promises to yield even more insights into the principles of evolutionary innovation and ecological adaptation. Each new discovery adds another piece to our understanding of how life responds to environmental challenges through creative modification of existing structures and behaviors. As we look toward the future of research on these remarkable creatures, we can be certain that they will continue to surprise and inspire us with their ingenuity and sophistication. Their story serves as a powerful testament to the limitless creative potential of evolutionary processes and the remarkable diversity of life that has flourished on our planet throughout its long and extraordinary history. The preservation of complete ecosystems containing these intimidation specialists has provided researchers with unprecedented insights into how their psychological warfare strategies functioned within complex ecological communities. We're talking about fossil sites that capture entire moments in prehistoric time, revealing not just individual specimens, but complete behavioral interactions between predators and their would-be prey. These remarkable fossil assemblages show us something absolutely extraordinary. In several locations, paleontologists have discovered what appear to be frozen moments of confrontation between massive clawed herbivores and formidable carnivorous dinosaurs. The positioning of the skeletons suggests that these encounters ended without actual combat, with predators apparently deciding that the potential meal wasn't worth the perceived risk. What makes these discoveries so incredible is that they provide direct evidence of the effectiveness of pure intimidation as a survival strategy. We can actually see instances where enormous predators, creatures that could have easily overpowered most other herbivores, chose to back down when faced with these theatrical displays of apparent weaponry. The behavioral ecology revealed by these sites is absolutely fascinating. The intimidation specialists weren't just randomly wandering around hoping to encounter predators they could scare off. Instead, they had developed sophisticated territorial behaviors that maximized the effectiveness of their defensive strategy while minimizing the energy costs of constant threat displays. Evidence suggests that these creatures established and maintained territories in areas that provided optimal sight lines for their defensive performances. They positioned themselves in locations where potential predators would encounter them, at distances that maximized the visual impact of their displays while providing sufficient space for dramatic posturing without immediate physical contact. The seasonal timing of their territorial behaviors appears to have been precisely calibrated to predation pressure cycles. During periods when carnivorous dinosaurs were most active and hungry, these herbivores intensified their defensive displays and territorial maintenance. When predation pressure decreased, they could afford to reduce their energy investment in intimidation and focus more resources on feeding and reproduction. From the tiniest precision hunters, no bigger than house cats, to the most colossal intimidation specialists wielding claws longer than swords, these remarkable creatures have shown us that evolution's creativity knows absolutely no bounds. We've journeyed through millions of years of prehistoric innovation, witnessing dinosaurs that transformed simple appendages into acoustic hunting systems, mechanical harvesters, psychological weapons, and precision excavation tools that would make modern engineers weep with envy. Their incredible diversity proves that when life faces survival challenges, it doesn't just find one solution. It explores every conceivable possibility, creating a spectacular array of evolutionary experiments that continue to astound scientists today. These clawed marvels remind us that the natural world operates by rules far more creative and audacious than anything we could imagine. And their legacy lives on in the birds soaring overhead, carrying forward the genetic innovations first perfected by these ancient masters of specialization.